Good morning. It's good to be here, giving a talk at Southern California ACS. I have given this type of talk before, mostly on Zoom because of the COVID issues. And today I'm going to tell you a story that we have been working on for many years at the Loker Hydrocarbon Research Institute for past 25, 30 years on what is called a one carbon problem. I look at the greenhouse problem as a simple one carbon problem. And we are trying to give a one carbon solution for a one carbon problem. You might have heard the concept called KISS principle. Keep it simple, stupid, or keep it simple, silly type ideas. Okay? I hope at the end of the day, I will convince you that this is a good idea. Now, what is happening in the world? There is increasing, population, and of course, everybody would like to live like an American. Increase in standard of living. And in fact, in a way, this has been possible for about 10 to 15% of the world's population because we burnt a lot of fossil fuels. Industrial revolution, we started burning coal, oil, and gas in enormous amounts. And of course, fossil fuels are hydrocarbons made of carbon and hydrogen. And once you burn it, carbon becomes carbon dioxide and the hydrogen becomes water. Okay? And these are finite, non-renewable on the human time scale. And this activity has led to increase in carbon dioxide content in the atmosphere. In fact, currently, it's about 422 parts per million. Pre-industrial revolution, it was around 250, 260 parts per million. So, we have almost going to double in the next 50 or so years, and this has detrimental effects. So what are the problems we are facing as a population? In 1650, the population of the world was about 500 million. And in 2011, we surpassed 7 billion. Very recently, we surpassed 8 billion. Okay? So population of the world is growing. And what modern population requires is energy. And in fact, we are continuously using about equivalent of 18,000 power plants operating at 1 gigawatt continuously. That is the consumption we are doing. All energies I'm talking about. Propulsion, heating, cooling, everything. If you compute, it's about so-called, 18 terawatts continuous. And this is supposed to go up by 21 terawatts by 2025, okay? This is a little bit old number. We are already in 2022. And this is supposed to go by 30 terawatts by 2050. And in fact, this is a slide, it's published from 2016. It's still kind of true because we had COVID and the fossil fuel consumption hasn't changed as much. If you really look at it, more than 80% of our energy comes from burning fossil fuels. Basically, oil, coal, natural gas, for example, and oil and coal are still, big. Natural gas is increasing. And if you look at renewables, non-carbon based, it's still not very much. Although we are making solar, wind and all happening, United States is making a lot of efforts in this direction. Europe has done much better than us, some of the European countries with renewables, okay? Of course, necessity is the mother of invention because America still has a lot of fossil fuels, okay? So the thing is, mostly it's fossil based, but fossil fuels, the way I define it to my students, it is fossilized sunshine. It's all sun's energy stored in carbon. If you understand that, as a chemist, we can come up with problems to manage carbon. Okay, that's what I'm going to talk about. Now, of course, the CO2 concentration has increased and it has led to global warming. We all know that. We have almost gone, like 2 degrees Fahrenheit. And this has, as you see, the change in weather patterns and all that, this is a big issue. So global warming is a big issue, but I don't want to go too much into this. You already know that. In fact, in northern hemisphere, the temperatures are going up. Okay. In fact, there was an article in Washington Post in 2019, August 20. The temperatures have gone up quite a bit. In fact, a large part of Canada, is at 2 degrees Celsius higher, which is amazing. So this is a big issue. Of course, if you really compute what's happening, the anthropogenic carbon dioxide emissions, the average between 2011 and 20 has been about 38.8 billion tons a year. Currently, last year, we surpassed about 41 billion tons of anthropogenic CO2 emissions. And half the CO2 ends up in water, making soda water, acidic water, ocean acidification, and this destroys coral reefs. This is a big issue. Once coral reefs goes, all kinds of the life in oceans change, and they're detrimental to their existence. And of course, rest of it also stays in the atmosphere, causing all these issues of global warming, ice melting, and and also ocean. The melting of glaciers is a big issue too. Low-lying areas are going to be flooded and all that. Now, the biggest culprit for global warming is carbon dioxide, okay? CO2, anthropogenic carbon emission. But another culprit is methane, the principal component of natural gas. Methane itself is about 23 to 25 times more global warming potential than CO2. And NOx, which comes out of your automobile emissions, diesel and gasoline engines, this is a big issue. And also so-called fluorine gases, which used to be freons for refrigerants. This is also a big problem, but this is not, that is 2%. And these are the sources, for CO2 emissions. And so what is the solution for that? And initially, people thought this best solution is an engineering solution. You basically capture CO2, separate it from air or point sources, coal burning power plants, cement plants, and all that, and bury it in depleted natural gas fields or depleted oil fields, deep aquifers, bury it under ocean under pressure. These are all engineering solutions. Of course, if you want to massively, bury CO2, this is the way to do. And there's another technique called mineralization. So you basically make into, limestone, reverse, but nature's engineering, which takes a lot of effort, okay? People are doing that too. But still, this is not that, well developed yet. And so just to give you some, numbers here, ladies and gentlemen, currently, we're using 100 million barrels of oil, petroleum oil a day. A barrel is almost 42 gallons, it's 160 liters, okay? So it's a lot of oil we are burning, 11 billion meter cubes of natural gas. We're still burning 20 million tons of coal, not as much in the United States, but in China and India, they're burning quite a bit of coal to generate electricity. So more than 40 billion tons of CO2 is released, we know that. And the solution that was given in the United States many years ago was we can make biofuels. In fact, one other thing America does, even in California, if you go to a gas station, you can see 10 to 15% blending of bioethanol, ethanol made from corn. In fact, US is producing around currently 17.3 billion gallons of ethanol, okay? 400 million barrels equivalent, okay? That is the number. And this is equivalent to 272 million barrels of oil. So if you really look at it, this ethanol coming from 40% of the corn crop. We are burning actually food here. So this is actually only 2.7 days supply. So it's a drop in the bucket. So you cannot, supplant fossil fuels. You can only supplement, This is the big issue we have. Of course, Brazil makes, ethanol from sugar. And if you really look at how much nature works hard to make these crops, in fact, in life cycle analysis, they are terrible. Okay, we shouldn't be doing this. Now, biodiesel requires a lot more land. In fact, vegetable oil as a diesel substitute, again, nature put so much effort to make it, and burning it, I think, is not a great idea. Okay. Now, biomass, CO2 fixation by photosynthesis. We all know this simple equation we talk about, photosynthesis with chlorophyll. CO2, H2O makes all these sugar type molecules. And these can be only a small percentage of our energy mix, because we need to worry about biomass and related fuels is land availability and use. Water resources is a big issue, irrigation. In California, we are facing a lot of drought lately. In fact, San Joaquin Valley, they wanted to, from vegetable cultivation, they wanted to grow sugarcane to make ethanol. It's so asinine because sugarcane requires a lot more water to raise this crop, So these are the things we need to worry about. And food security versus energy security. And fertilizer use. Nitrogen fertilizers made from ammonia, and the hydrogen comes from natural gas reforming. So we need to think about whole life cycle when you're doing this kind of stuff. And processing technologies, overall energy balance. So I'm telling there is a big problem here, using biomass. But let's not despair. Sun is the source of all energy on Earth. For past, present, and foreseeable future, next 4.5 billion years, sun is going to be there. And sun puts out enormous amount of energy on Earth, almost 173,000 terawatts continuous. It's a reliable nuclear fusion reactor far away. So we don't have an energy problem per se. We have energy storage and energy carrier problems. Okay, we have all this alternative energies, hydropower, geothermal energy, wind energy, solar, biomass. We can do all this, even nuclear if you have stomach for it. The problem is, why don't we use these alternative energies in a large scale? The main, actually costs are coming down rapidly, especially solar panels, wind energy are becoming quite cheap. But fossil fuels are still the biggest bargain nature ever gave us. The most promising solar and wind are intermittent and fluctuating. They mostly produce electricity, and the storage of electricity is a big issue. Battery deployment, although people talk about it, is still infantile. We haven't done much on that. It's very difficult to do, because if you don't have batteries to store energy, you cannot maintain your grid properly. Grid maintenance, the voltage stability is very important. You have to have storage. So this is a big issue. So this is just to show you guys that solar is 23,000 terawatt year per year. It's a huge amount is coming compared to all other things like, if you look at total coal, total reserve is only this much, 900, terawatt year per year. It's a terawatt year total, uranium, petroleum, natural gas, and also here I have the wind. Wind is regenerated because the sun's heat, makes the wind go, right? So all these things, so we don't per se have an energy problem. There's plenty of energy coming on Earth. So everybody talks about, one of the things is hydrogen economy. Look, hydrogen is clean, non-carbon based and all that. Hydrogen is not a primary energy carrier on Earth. Its boiling point is minus 253 degrees Celsius. It's abundant in the universe. It's a very primordial molecule, right? We know that. On Earth, it is tied up in water and fossil fuels. It needs to be liberated. You need energy for that. It's incompatible with 20% oxygen in the air. And liquid hydrogen has 1/3 volumetric energy density of gasoline. This is a big issue. 2 grams occupy 22.4 liters. So it's a very voluminous material. Infrastructure is very expensive. All metals which contain carbon beyond 5,000 psi become brittle. So storage is very expensive. If you want to put 10,000 psi hydrogen in a cylinder, you need a carbon composite tank. So that's a big issue too. Highly flammable with a colorless flame. So if really these are some numbers. Methanol has only 22 millijoules per kilogram of energy. Look at hydrogen. Hydrogen is 142 millijoules per kilogram. But if you go to, and current production of hydrogen, just to give you some numbers, it's 70 million, metric tons, and 76% is still coming from steam methane reforming, natural gas, and 22% come from coal gasification, mostly in China, and electrolysis is only 2%. So renewable hydrogen is only 4%. Okay, there are not very much in this whole space. People are doing it differently, and also you can reform biomass too to get hydrogen. So hydrogen is not produced in large quantity yet, green hydrogen only. So we can even talk about nature of hydrogen. In fact, I wrote a report to this International Renewable Energy Agency last year, a 177-page report. We classify hydrogen like green hydrogen, blue hydrogen, gray hydrogen, low carbon intensity, high carbon intensity, and things like that. Okay, so we know what kind of hydrogens we are currently producing. And the thing is, the cost of green hydrogen, in fact, what DOE wants is by 2050, it should be 90 cents to $2 a kilogram. And this is a challenge, okay? People are thinking about it. It has not happened yet. Now, if you really look at compressed hydrogen gas, including, for example, liquid hydrogen at minus 253, the volumetric energy density is much less than other fuels. For example, methanol is much better than liquid hydrogen. So if you have 1 liter of liquid hydrogen, which is very difficult to lug around because minus 253 degrees, 1 liter of methanol has a lot more energy than hydrogen, okay? And in fact, Methanol green hydrogen carrier is 99 gram hydrogen per liter it carries. Okay, so methanol itself is a good hydrogen storage medium, better than hydrogen itself in terms of volume. That's what I'm trying to convey here. Okay, so most of the hydrogen is used for oil refining, ammonia synthesis. You make fertilizers like urea. It's a big shot. And methanol, only 10% is hydrogen is utilized to make methanol. It's not all green. It's all mostly brown methanol, not green methanol. Okay, fossil based. So as a chemist, as an organic chemist, for me, carbon dioxide is not a problem. Carbon dioxide is a freely available, very democratic feedstock because air is everywhere. Every country has access to air. And there are 420 ppm of CO2. So if you extract CO2 from air, anybody can extract anywhere. You know, oil is in Saudi Arabia, Texas, but air is everywhere. So it's very democratic. So CO2 is a good source everywhere available. So, but CO2, we can make all kinds of interesting chemicals and products out of it. In fact, we all use dry ice, which is used. We have, for example, soda water mixing with our drinks. You can make polymers with it, and it's used in massive quantity. It's used for oil recovery, fertilizer, but you can make platform chemicals like methanol, formic acid, methane, dimethyl ether, dimethyl carbonate, etc. So you can make liquid fuels, energy storage, you can make synthetic hydrocarbons. So CO2, in my opinion, is a fantastic feedstock. And based on these kind of ideas, tongue-in-cheek, about 25 to 30 years ago, we proposed a concept called the methanol economy. How from one simple molecule, the wood alcohol, we can develop a whole economy with it to replace petroleum oil and things like that. Once you make green methanol, you can do this continuously because it's carbon neutral. It's not harmful. That's the idea. And with my late colleague Giorgiola, who passed away in 2017, we came up with this concept. And as you all know, that he won the 1994 Nobel Prize in chemistry for his work on carbocation chemistry. I was trained as a physical organic chemist working with George. So methanol, so-called wood alcohol, wood spirit, it was discovered by Jean-Baptiste Dumas and Eugene Pelligot, isolated in 1834. It's called the wood spirit. You take wood, do destructive distillation, the methanol comes out, okay? And that's how it was isolated. The only problem with methanol is it's a very, it has a good smell, but it is poisonous to drink, okay? But how many times you go to gas station and ask for a pint of gasoline, a diesel to drink? You don't do that either, right? So methanol is, you shouldn't drink it, but in small amount it's not toxic. In fact, if you drink orange juice, there is very little methanol in it. Beer has methanol naturally when you brew it and all that. So in small, and the antidote for methanol poisoning is ethanol, okay? So methanol is a fantastic fuel for internal combustion engine. It's a high octane fuel. It's clean burning, inability to detonate. It's a 17.4 millijoules per liter energy. It can be blended with gasoline in all proportions. It's a liquid hydrogen carrier. And methanol can be converted to dimethyl ether. It's a diesel fuel substitute, high cetane value diesel. And it can replace LNG and LPG. I just wanted to let you know, Los Angeles City is going to ban use of natural gas in cooking. Did you hear that? Because natural gas is methane, which is 23 to 25 times more global warming potential than CO2. Dimethyl ether could replace natural gas for cooking, and it has a global warming potential same as CO2. So if you make methanol economy, we can also come up with cooking fuel with dimethyl ether, which you can put LPG substitute. So all these things are happening as we speak. And methanol could be used in direct methanol fuel cells, which we were involved in inventing this technology. And methanol can be converted to ethylene, propylene, gasoline, diesel, and etc. So it can do many things. So I'll tell you a little bit about that. So methanol, excellent internal combustion engine turbine fuel, liquid, 64.7 degrees. It was used all in race cars. All race cars since 1950 used methanol, and also you can blend it with gasoline. In fact, in Los Angeles in the late 80s, the AQMD experimented 85% methanol, 15% gasoline, because we had a smog problem. So it was a successful project, but the The operation was successful, the patient died. Because Arco Petroleum came up with an additive called MTBE, and they said that we don't have to do M85 anymore. So they gave up, which we could have done in California in the late 80s. And half the volumetric energy content of gasoline, but it's more efficient, cleaner burning. It can be blended in biodiesel. It's an excellent hydrogen carrier. I may tell you a little about that if time permits. Of course, it's corrosive like any other alcoholic fuel, but we already have flex fuel vehicles. It's not a problem. Methanol has low vapor pressure. You have to spike it with gasoline. Ingestion is a problem, but dispensing is not a problem because China is doing this on a massive scale. Spillage, all low-level organisms can decompose methanol. It's not a problem. In fact, wastewater treatment plants in Los Angeles, they use for denitrification copious amounts of methanol. Methanol is a reducing agent. Okay? So it's already utilized for wastewater treatment. It's not a problem. So methanol in internal combustion engine, it gives you a very high compression ratio, 15:1, whereas diesel is 12:1, gasoline is 8:1. So you get enormous torque in methanol engines. It's a higher latent heat of vaporization. That means it takes heat away from the engine. No nitrogen oxides are formed. Since it's a one carbon alcohol, no black matter, no particulate emission. So for cities like Shanghai, New Delhi and all that, methanol will be a fantastic fuel because emissions are better from your IC engines. And also when you have fires, methanol fire can be extinguished with water, where a gasoline fires you need a foam. This is another advantage with methanol. And you can mix it with ethanol, methanol, you can do all that. People have done that. And it's already dispensed in China in big way. In fact, China is the biggest practitioner of methanol economy based on a book we proposed, and it was translated into Chinese. I'll come back to this in the end. China is blending coal-based methanol. 9% of transportation fuel in China is methanol. The Geely car company has made about 250,000 vehicles running in Shanghai, which are M100 fuel. So it's all dispensed in gas stations and all that. Israel is trying to do that. Iceland, I'll tell you a little bit about that. They produce what is called renewable methanol, called Volcanol, based on geothermal electricity already. And I named that plant Georgiola Renewable Methanol Plant in Iceland, which is making 12 tons of renewable methanol a day. So if a diesel is a good substitute, in fact, if you have a diesel engine like 15-liter diesel engine gives you 2,000 pound-feet torque, okay? A 9-liter methanol engine gives you 2,000. So you can make engines smaller for diesel engines. Okay, diesel substitute engines for diesel engines are bigger, methanol engines are smaller. So this is a game changer for heavy transportation. Okay, so this has been done by Daniel Cohn at MIT because methanol provides extremely strong suppression of engine knock, gives very high turbocharging, and spark ignition is required for that. In fact, one of the biggest applications is happening as we speak today is methanol is going to replace bunker fuel. About 370 million tons of bunker oil is utilized in shipping industry. Dirty fuel, okay? So they want to make the shipping lanes greener. There's a big push on that. And bunker oil has highly polluting SOx, NOx, and particulate emissions. So methanol is used in the emission control area. Stena, a Swedish ship, completely converted to methanol engines. Methanex, which is the producer of methanol, used trawlers which are powered by methanol. And engines can be easily converted to methanol burning engines by putting Glowplex in diesel engines. This is happening as we speak. Maersk, which is the largest shipping company, this year ordered 8 large ships worth $1.5 billion. They want to use renewable methanol as a fuel. Now, methanol can be converted to dimethyl ether. I already said it's a high cetane value diesel substitute, very clean burning, already used in spray dispensers, non-toxic, does not form peroxides, substitute for LNG, LPG, easy to produce, ship, and dispense. It's almost like a liquefied propane gas, sootless flame for glass blowing, and trucks are running all over the world on DME. Now, you can also use methanol to make hydrogen for hydrogen fuel cells. In fact, these are called range extenders, where methanol is reformed to hydrogen CO2 mixture through a fuel cell. So a 150 kilometer vehicle can go to 800 kilometers. Instead of putting hydrogen, you put methanol. On board, you make hydrogen, run a fuel cell, charge a battery. These kind of technologies are also becoming great in this area. And methanol stores about 12.18% hydrogen. Just to give us flavor, here when you reform methanol, you got CO2 and hydrogen. But we don't want to spew CO2 into atmosphere. So my group developed a very interesting chemistry where methanol and a primary diamine, we can reform it to make urea and 3 hydrogen. And urea can be converted back to methanol with a catalyst with hydrogen. So it's a way to store hydrogen. And we were able to store 6.6% hydrogen in these kind of ideas. In fact, this is better than DOE target of more than 5%. We already reached this, okay? We had a nice publication in JACS on this many years ago. And more lately, we have done this. In fact, we can reform methanol with a base and a catalyst. We get pure hydrogen, and the carbon remains in the solution. So we don't have, we can produce hydrogen on demand at a site, and we can make pressures up to 450 bars. So basically, the chemistry at 120 degrees, it generates pressure, hydrogen pressure. No carbon is released, so we can produce hydrogen from methanol. And this will be a game changer. We call them chemical compressors. Now we can also use methanol in a direct oxidation fuel cell. You have an anode and a cathode. We found that methanol, water, and platinum ruthenium can be oxidized, and at low potential, and protons and electrons, can be reduced with oxygen, on the other side at the cathode. So overall potential is 1.2 volts. And this project was done with the Jet Propulsion Laboratory, and we had many collaborators with DARPA in the 1990s. I just want to stop here and show you. This is the heart of a fuel cell. It's called a membrane electrode assembly. You have an anode and a cathode with a proprietary membrane, a proton conducting membrane that was developed in our laboratory many years ago. And I just wanted to show you how simple the technology is. This membrane electrode assembly is between 2 polycarbonate plates. And what I'm going to do is I'm going to take some methanol and water, which I brought it. I usually take this in my shaving kit when I travel in the airplane. My UD colon, I call it. And I'm going to pump some methanol and water into this little toy and see what it does. It starts making electricity at room temperature. So this has been commercialized actually. Maybe I should just leave it here so you guys can watch it. This will run till tomorrow morning. So, method is a 5 kilowatt hours per liter theoretical energy density, and we can harness half of it already with this technology. And Smart Fuel Cells in Germany making devices from 70 watt hours to 3 kilowatt hours portable devices. And you can also use methanol in a solid oxide fuel cell. This is again similar, very easy to do. And Wärtsilä in Finland and all that, they have done 20 kilowatt methanol state of solid oxide fuel cell, which is used in shipping industry already. Methanol could also be used to cook. Kerosene is very dirty, and China used to use coal for cooking. Chinese hotels and all that, they use now methanol. 3 million tons of methanol is used for cooking because it is so clean burning. Okay, so it's becoming very big for cooking. You can make steam with boilers. 1,000 boilers in China uses 1 million metric tons of methanol. So it's already utilized. They're all brown methanol. They're made from coal, but they're already getting ready for using this methanol economy concepts, which is what we want to do. Now you can also produce in turbines electricity in Eilat, Israel. They generate 50 megawatt power plant, which uses methanol. So the emissions are very clean in that town. You can do electricity generated fuel cells. You can use it as a cooking fuel. You can feed it to bacteria to make tofu-like proteins as animal feeds. In 1960, ICI, one of the largest chemical company in those days, made 100,000 tons of animal feed using methanol as a starting material, like tofu-like product. Currently, 107 million tons of methanol is produced, and mostly it is derived from either coal or natural gas. Not that much renewable methanol yet. It's a commodity chemical. It is used to make acetic acid, formaldehyde. You can make ethylene, propylene. This is a big area right now. Gasoline blending, MTBE, biodiesel. These are other applications. So basically, it's a platform chemical, commodity chemical. So people know how to deal with it. China makes almost close to 29 million tons of ethylene propylene through methanol commercially. So this is an import substitution for them. They don't have to import naphtha. They're converting coal into olefins. This is the technology they have developed. It's MTO process. My institute did all the mechanistic investigations in the 80s. How C1 becomes C2. That mystery we solved with labeling and things like that. So we wrote a report. Again, I told you this renewable methanol report. Coal is 35% methanol, and so mostly practically all of it comes from fossil fuels. Biomass and renewable is less than 1%. So this is very interesting. Not much green methanol is produced. In fact, most of it we call it brown methanol or blue methanol. E-methanol or biomethanol, these are all green. So there is different green content. We kind of gave a gradation. And methanol is basically taking CO and 2 hydrogen, you can make methanol, exothermic process. CO2 plus 3H2, again make methanol, it's exothermic. And there's a water gas shift reaction. Okay, these are all some chemistry that happens when you're doing methanol synthesis. And steam methane reforming gives CO3H2, endothermic. You can do partial oxidation, or also you can do dry reforming, which is highly endothermic. So a combination of steam and dry reforming, we came up with a process called bioreforming of methane. Okay, methane, water, and CO2, we can make right ratio of syngas to make methanol. So this utilizes CO2 for reforming process, and in fact we have developed a lot of chemistry in this kind of efficient utilization of natural gas to make methanol. And we also came up with a process called oxidative bioreforming, where methane and oxygen can be oxidized, simple burning basically, very exothermic. Then we take the effluent of this, mix it with methane, you get the right ratio of syngas to make methanol. This is endothermic. So we can take the exothermicity of this reaction to take care of the endothermicity of the second process. So the overall process, if you look at it, is highly exothermic, methane and oxygen. So this will be a game changer for methanol synthesis from natural gas, where you can do cogeneration. You can make methanol and also produce steam to make electricity and all that. 30% better than the commercial processes. And there's a lot of interest to commercialize this, which was done in my institute. Of course, China uses coal. For every molecule of 3 carbon molecules, they make 2 CO2 and methanol. Okay, but China makes, they have mastered this from low quality coal, high ash content. So they gasify it, make methanol, and they have a huge industry based on coal, methanol industry. Now, methanol can also be made from any biomass, non-edible. You can gasify it, make syngas, and make methanol. And but biomass alone cannot fulfill our increasing energy needs. You can take lignocellulose, fast pyrolysis, you get condensate. You do gasification with pure oxygen, you get syngas. You can get methanol as liquids. And this is being practiced, for example, effluent of paper industry. You can take it, black liquor that you can get, you can make syngas and dimethyl ether. This was practiced in Kemrek in Sweden, 4 tons per day bio-DME. And in fact, from glycerol, you can gasify it. There's a 200,000 kiloton year capacity in Netherlands, bio-MCN. So people are making from bio sources also methanol. Now, the ultimate source for carbon to make methanol is, of course, CO2. CO2 is very stable, of course, that's why it's out there. Every carbon goes to CO2. Difficult to reduce, it's a trace gas, okay? With declining fossil fuel reserves, CO2 will become the best source of carbon for humankind. And in fact, there are various sources. CO2 is released, geothermal vents, fermentation processes, cement plants, fossil fuel burning power plants, and all that. And there are many processes already to recover. Our group at Loker Institute developed some silica-based, polyethylene-based, cross-linked supports to capture CO2. And this, you just pass air over it. And by this chemistry, you can capture CO2. In fact, we have published in this. I don't want to go too much into this. You just pass air at room temperature. The CO2 is absorbed. If you have humidity, it can be more efficient. We can actually take 78 milligrams per gram of this adsorbent. Works really well. And this has been, you can absorb, dissolve thousands of cycles. We have done that. And this has been utilized for indoor air capture. We have already licensed this technology. Our materials are made in multi-ton quantities. for CO2 capture. And this has been deployed in 300 high-rise buildings, including Empire State Building, Goldman Sachs, and places like that, okay? For indoor CO2, so you can save 30% energy costs in a building like this. So you don't have to cool or heat, your air, the air handling. You don't have to move as much air. So the CO2 is grabbed within the building. Because you and I, on average, basically, exhale close to 1 kilogram of CO2 over 24-hour period. Okay? So the idea is, why don't we capture this CO2, green hydrogen, make methanol? This is what the methanol economy is all about. And in fact, just to show you, we have come up with a technique called CO2. You can capture, desorption, compression. This requires a lot of energy. So my group has taken CO2, we capture it, put hydrogen, make methanol, so then the base is regenerated for second capture. We call this integrated capture and utilization. One carbon problem, one carbon solution. And in fact, you can do CO2 reduction with a variety of techniques. Hydrogen is a good reducing agent. There are a lot of catalysis. You can use thermochemical, electrochemical, photochemical routes. So what we have done, we can take amines, capture CO2 from air, hydrogen, make methanol. The amine is regenerated for subsequent capture. We call this as integrated capture and conversion. Very easy, so we don't have to desorb. In fact, we have done amine capture, hydroxide capture, and lately our paper in 2020 got a lot of publicity. It made the front cover of JACS. And we do a lot of homogeneous and heterogeneous catalysts. You can see different types of catalysts. And we can get almost 100% conversion with certain catalysts, the CO2 that is captured from air. So this will be a game changer, integrated capture and conversion. And in fact, this also made the cover of JACS, and CNE News covered it. So we believe that we have tiger by the tail. The integrated capture and conversion of carbon dioxide is the way to go, make methanol and other products. And we also can use heterogeneous catalysts to do that. And this was published, in 2021, last year. So you can also do water electrolysis. It's a very mature process. At 4 cents a kilowatt hour, you can do, for example, $2.6 a kg hydrogen could be produced, and this can be converted to methanol. And at 4 cents a kilowatt hour, the cost of methanol will be $1.8 per gallon. In fact, this is done in Iceland. Geothermal CO2, which comes from geothermal steam. Geothermal electricity makes hydrogen, and we make methanol, and we called it volcanol. It's a volcanic origin, the heat. So, and this plant is named after George Olah, my colleague, who passed away in 2017. And so they're able to make 12 tons a day. This is 90% reduction in CO2 emissions compared to gasoline. It's almost a green methanol. It's already being practiced. And China, just last week, in Anyang, in the Henan province, just established a first commercial scale 110,000 tons per year CO2 to methanol plant. It started production. Same technology as Carbon Recycling International in Iceland. And their hydrogen is coming from coke oven gas by basically some kind of a water gas shift process. Okay? So it's very interesting. So what I've been telling you, ladies and gentlemen, is methanol, this simple molecule, wood alcohol, can be made from natural gas, coal. These are all fossil. It can be made from biomass. Ultimately, it can be made from CO2 with green hydrogen, and this can be converted to dimethyl ether. This I call the KISS principle, a very simple idea to solve our global problem. If carbon is a problem, carbon has to be the solution. We have to learn from nature. Remember, you and I are made of carbon. So we cannot divest from carbon. We need to manage carbon. That is the take-home message. Nature does it so beautifully, but we can do through chemistry much better, more efficiently. Simple processes. So this is what I'm talking about, ladies and gentlemen, for the past 40 minutes. Renewable energy is the way to store energy. And CO2, hydrogen you can make. And you can keep on doing. The beauty of methanol economy is you don't have to change your infrastructure. Now everybody wants to go electric. But nobody does the life cycle analysis on electric. How much carbon you're going to put in, making all those batteries. and building all these cars in Tesla and other places. They're wonderful machines, but keeping existing IC engines for transportation is critical. And we can make, instead of changing the whole technology, let's go to renewable fuels. We can do it today. That's what the take-home message is. And we wrote a book, third edition actually, 2006 was our first edition, called Beyond Oil and Gas, the Methanol Economy. And that got translated to Chinese right away. It's translated into Japanese, Russian, Hungarian, Swedish, and the Chinese took good advantage of this idea. In fact, Chinese called methanol as a sunshine fuel or something like that. Yeah, it's very interesting. So why haven't we done in America? Because we still have a lot of oil and gas. Our society is developed on immediate profits and immediate gratification. Winston Churchill made a very famous remark during Second World War in America. Americans will do the right thing in the end after exhausting all other alternatives. Okay, hopefully we'll do that. Okay, with that, let me acknowledge my colleagues who contributed to this project. This is a long-running project at my institute. And of course, late George Ola, I'm very grateful, and Marshall, John Paul, and all these people contributed. Even Thomas Matthew, our current chair, participated in this program. And we have some students in the audience. Lakshman is here. Actually, he's working for an industry. They're here. And so it's very nice that they are here, and all this support came from my NSF, US Department of Energy, DARPA, RPE, my institute, and all that. With that, this is our group. About 2 years ago, we took a picture in sunny Southern California. With that, thank you very much for your kind attention. I'll be happy to answer some questions.